Good morning, everybody. My name is Wannes van der Stappen. I work at Larian. I'm a senior graphics programmer for 14 years now at Larian. I will be talking about our road towards Baldur's Gate 3 as a graphics team. When you look at our game, you only see the visual side, so the outside, the rendering features there. But there's always a lot of things happening behind the scenes, and as most of you know, that can be quite a lot, but it's different for every game. So I thought it would be nice to give an overview and hopefully answer some questions such as, like, why did you implement this feature, or why didn't you implement that other feature? So in this presentation, I will be looking back at our entire development cycle, and I hope that it will provide some insights. So, talk overview. First, short introduction. Who are we? Then I'll go over the requirements and goals for Baldur's Gate 3. Then I'll talk about the road itself. So first, the adaptation of the more modern APIs, then new and improved rendering features, then technical changes and optimizations, and then there will be a conclusion. I'll go over what went right, what could have gone better, and then maybe a small thing about the future as well. And then hopefully there's some time for Q&A. So, first, introduction. Who are we? So we are Larian Studios. We are located in 7 different countries, with Warsaw, well, that's our latest studio that opened this year. We have our own in-house engine, which we publicly call the Divinity engine, and internally we call it Framework. As usual, programmers, it's the hardest task of a programmer to name things. So that's obviously made by the engine team. The graphics core team was about 5 people in the beginning of development, and it grew to around 10 people. It's quite hard to put a exact number on it, because some people work across different departments a bit. We also have our custom toolset, which is obviously made by the tools team, but also the tech art team. They are responsible for our importers, exporters, and anything that's related to our DCC tools that we use. And of course, there's a lot of collaboration with all the other teams. These are some of the games that we made. So we are known for the Divinity series, with the latest Divinity game being Original Sin 2. And of course, we also released Baldur's Gate last year. So with all these, well, this engine has seen several iterations. The first one was used for Dragon Commander, and the last one for Baldur's Gate 3. And on the right, you can see all the platforms that these games are released on. With all those platforms, obviously, there's also a lot of APIs that we need to support. So for PC, we shipped with DirectX 11 and Vulkan. For macOS, we used Metal. For Xbox Series, we used DirectX 12. And for PS5, well, they're a proprietary API. I will be mostly focusing on DirectX 11 and Vulkan and DirectX 12, but some general concepts will, of course, also apply to the other APIs. So what were our requirements and goals for Baldur's Gate 3? So our starting point was obviously the original Sin 2 Definitive Edition. This was also a big RPG world, but this was made with a much smaller team. And because of that, the game was more stylized than Baldur's Gate 3. So we had lower detail models and textures. High fidelity was simply also not needed because of the camera perspective, which was top-down. The cinematics, well, we didn't have cinematics. It was, the dialogues were also just top-down. No other camera changes were involved. So the characters also didn't need much extra detail. And you could zoom in a bit. The camera was a bit more horizontal then, but even then, you couldn't really see that far. So because of this game design, many things were simply not needed in our engine. We only had basic culling, so just frustum culling, distance culling, and culling some small objects. We even didn't have instanced rendering, simply because, well, we didn't need it to fit everything within the performance budget. And fun fact, the meshes didn't even have LODs. So our engine did support this, but no different quality levels of models were made. Apparently, we did forget to remove this, though. But apparently, for some people, this also works as a placebo. So what was our visual target for Baldur's Gate 3? Well, obviously, everything needs to be more detailed meshes, more detailed textures. But we also wanted to make better use of PBR, because this was introduced quite late in the previous project. We also wanted denser and larger worlds and more horizontal camera angles. This means we will have larger view distances. And then, of course, perhaps the biggest part that was new for us was cinematics and cinematic dialogues. So this required a lot of features because we will have close-ups of characters equals more detail. And we also need better shading and materials. And there was a lot of new tech involved in this across all other departments as well, of course. And so, yeah, what were our, well, we started using LOTs in case anybody was wondering. So what were the technical requirements for graphics? So, well, of course, we need to implement all the visual targets, but also keep everything within the performance budget. So we need to add a lot, but also optimize a lot then. So we had a few planned features. We wanted built-in tools for LOTs and not have artists do it in their DCC tools. We wanted hierarchical LOTs. We wanted to, of course, use instance rendering now, occlusion culling, virtual texturing, and the list was way longer. And yeah, also Vulkan, DirectX 12, PS5, and Metal. This was all new. So a lot of work to do. So I'll explain our road that we took. So first, the adaptation of the modern APIs. I put modern in quotes because, as some of you know, DirectX 12 is almost 10 years old now. So the first question that we often get is, why did you use Vulkan on PC when you need to support DirectX 12 anyway for the Xbox Series? And well, there's a simple answer for that, Stadia. As some of you may remember, Baldur's Gate shipped in early access on PC and Google Stadia. Google Stadia needed Vulkan. And because we shipped in early access, this also means a shorter release time frame. The consoles were only planned for full release. And also, Vulkan had a bit of a wider hardware support than DirectX 12. So we went for Vulkan as our main API. So naturally, there's a second question then that people ask, which is, why are you still using DirectX 11 then? And well, things didn't really go according to plan. So what was the problem? BG3 was actually in full production already. The engine code team only moved to BG3 after pre-production happened, because we were still working on the definitive edition of Original Sin 2, which is aka the console versions. So the whole company was actively using a DirectX 11 toolset, which means that we couldn't break anything while replacing DirectX 11 with Vulkan. Well, break temporarily, of course. So we tried, but failed to use the following solution. We tried working on a different code branch, but the code diverged very quickly, and it was very hard to merge in new features that we did on the main branch, and so we tried to do new features on the new branch, but then our other departments were waiting for those features way longer. So that didn't really work well, so we merged back to main as soon as possible, and yeah, problem was fixed. Well, not really. This is kind of what we ended up in. So new features kept on being made, and we kept on fixing the Vulkan version. And well, you might think, like, why was switching to Vulkan so hard? Well, not because Vulkan is difficult, because, well, it's obviously a bit more complex than DirectX 11, but mostly because other programmers, firstly, they weren't using the Vulkan build yet, so we noticed issues much later. So we kindly encouraged them to use it. And nobody else wanted to use a less stable toolset. And, well, we couldn't really force them to do so, because this would cost production time. If everybody keeps crashing more often, you don't want that to happen. So this was not so easy to fix. So we ended up in this vicious cycle where nobody was using the Vulkan toolset, which means it wasn't really stress tested, which means that Vulkan was not stable, which means, well, and so on. So you might ask the question, well, didn't you have QA? Well, of course we had. We even added a new team called Tech QA. So they test all our code features that we add before they even end up in our internal builds. And yeah, that works really well. But, well, they were also testing other stuff. There's a lot of new features that needed to be added for early access. And in fact, that was also true after early access. So we didn't really find a good time to switch internally our toolset. And because also we basically had the same issue. There were a lot of new features that needed to be made. And so in the end, because we had a DirectX 11 toolset, our Vulkan version always had the same feature set. We couldn't add new features that only were possible with the newer APIs, because yeah, everybody was developing with the DirectX 11 toolset. Also, shipping Vulkan was a little bit scary because, yeah, well, it worked, but obviously it's a bit more prone to crashes than DirectX 11. So we released DirectX 11 as a backup. Vulkan was still the default, though. And what about DirectX 12? Well, this was simply not worth the risk, because it would have the same feature set again and just need more support from our side for no real reason. So how about our common rendering interface? Well, we didn't want diverging code between the different APIs, so we tried to use the same high-level code for all the APIs. There were some if-defs here and there where it was really needed, but overall this means that we had a bit of a mix of a DirectX 11 style way of working and also more modern concepts. So I'll briefly go over them now. So what about pipeline state? Well, we had an abstraction for this. For Vulkan, this then maps to the VK pipeline. For DirectX 12, the D3, D12 pipeline state. For DirectX 11, we just stored a description that we use normally to make these pipeline states. And so some pseudocode, this basically looked like this in our high-level code. And then for DirectX 11, it's simply translated into all the different context calls. We also had a DirectX 11 legacy fallback code path, which is, well, this. So set shader, set primitive topology, set rasterizer state, and so on. So what did this mean for the newer APIs? Well, construct a pipeline. We need to construct a pipeline description from this, and then we create the PSO right before drawing, and keep it for later, obviously, because creating PSOs, well, compiling them at runtime is super slow. But this code path was almost never hit. This was only in very, very rare cases where some edge case somewhere in gameplay needed to change some state. And because, of course, compiling PSOs at runtime is so slow, we had an abstract PSO cache. So this is generated offline. It's an abstract API-agnostic cache of all the possible PSOs that our game can have. This was derived from all the data that we have, so all the visuals, all the materials. And for Vulkan, we use this cache on the client machines at first startup to precompile all the pipelines. For DirectX 12, these PSOs could already be precompiled offline and shipped directly. And what does this mean at runtime? Well, we hash the description that we have of the pipeline. We check if we already created this PSO. If we did, we'll use it. If we didn't, then it can be fetched from the, simply from the cache. If not, in the worst case, we compile it at runtime, but again, I don't think we saw this happen a lot. Our code for resource binding was still very much DirectX 11 style, so we did have a set pipeline state call, but we still did we still set individual resources separately, like set constant buffers, set textures, set sampler state, and so on. We couldn't really use a bindless model because, well, again, we needed to support DirectX 11, and we didn't want to branch the code too much. This binding contains information about register index for DirectX, binding index and descriptor set index for Vulkan. And these are, in fact, automatically generated, which we'll see later. And yeah, there's a texture binding info for textures because we need a little bit more information than just what texture is it. We need to know if it's UAV or SRV and so on. Then we have an apply call as well before drawing. For DirectX 11, this then checks which registers changed. It then calls for text shader, pixel shader, and so on, set shader resources or set constant buffers and so on the context. For DirectX 12, our resource views, they live on the CPU side descriptor heap, and they are copied to GPU side descriptor heap right before drawing in the right order, so it matches the root signature. And then for Vulkan, we dynamically create unique descriptor sets using a hash, and they are destroyed if they aren't used anymore for X amount of frames. This is, of course, not ideal, but we didn't really have time to convert this into a more modern API where DirectX 11 then did separate things under the hood. Then shader compilation. To compile shaders, to generate shader files, we have a tool called Shader File Generator. Again, great names. Or SFG for short. This wraps different compilers. So for DirectX 11, 12, Vulkan, and PS5, we're all using HLSL. Only for Metal, we're using MSL. It outputs binary shader files and a shader reflection file. So for DirectX 11, we use FXC. DirectX 12 uses DXC, Vulkan as well, plus SPIR-V cross as well. And then these reflection files are used in CodeGen to generate these bindings that I talked about earlier. These are only used for our engine shaders, though, so the hard-coded ones in our framework for lighting, post-processing, and so on. Materials, on the other hand, they embed the binding info directly in the main material file data. So we have a lot of materials. We have a node graph-based system, and our artists, I think they created around 500 or 600 different materials, so that's a lot of shaders, a lot of PSOs. But if you want to know more about how these bindings are generated, there's a Vulkanized 2021 talk about my colleague Mikhail, who worked on this. So yeah, you can go to this link if you want to know more. Then there's render pass and frame buffer. These are Vulkan concepts. We did expose these to our higher level code because it would make things just easier for us if we did so. For DirectX 11 and 12, our begin render pass call, it simply clears the render targets or depth stencil if needed. The begin render subpass then sets the render targets or depth stencil, and end render pass just does some state tracking and handles some barriers in DirectX 12. And these calls also manage the viewport. Then about the CPU side still a bit, the command buffer recording. So this is an example of DirectX 11. Don't mind all those gaps on the other threads. This was captured on a Threadripper with way too many cores. But the red part is basically culling and animation updates. After that, we have some sort of fake command buffer for DirectX 11 to offload all of the work that is not related to, well, that is not the actual context calls themselves. But then, of course, on the main thread, we need to do all those context calls still, so it takes quite some time. But for Vulkan, for example, this was a big win because we could directly record the commands on the worker threads, and then we just had a little bit of submit time on the main thread. So now on to the second part, which is new and improved rendering features. So these are the things that most people usually see in the game. But there's also some interesting things there, some decisions that we had to make, well, some things were just simply consequences of new things that we added, so I thought it would be interesting to go over these. Some early tests. This is one of the first characters that we imported in our new framework as an attempt to improve quality. Of course, this doesn't look that great. So the skin looks a bit like plastic. The hair looks pretty bad as well. There's bad sorting going on. The eyes look kind of dead. There's shadow and light leaking issues everywhere. But we found out that we could actually tweak our lighting settings and make it already look a lot better. But there was still a lot of work to do. So we added some new shading models. So we added a skin shading model. I put the references at the bottom, and at the end of the slides, there's all the links. So we added separable surface scattering, translucency, and then it also uses a dual lobe specular. And in addition, for characters, we also have a very specialized material graph that uses different masks to control different parts of the character's skin, like the blood, the veins, the yellowness, and so on. So there's a lot of customization possible for character creation. Then we have a translucent shading model, which is basically the same translucency as in the skin shading model. Then we also added a hair shading model. So there was a lot of collaboration with the artists for this, because every time we made a change, they, of course, also needed to reevaluate the different hairstyles that they already made. So there was a lot of, So there was a lot of work going into this, and there's definitely some improvements still possible there. But we also added a cloth shading model. This was done quite late in development, but that was done because we felt like something was still missing, like the hair looked better, the skin looked better, and so on. But yeah, the materials on the armors could also look a bit better still, so we added this cloth shading model. But that meant that we had now a pretty long list of shading models. So the first 3 we already had, then the next 4 I just showed you. And then cloth hybrid is basically, well, it allows artists to blend between cloth and a regular default shading model. But this meant very expensive branches in our clustered lighting paths. So we added tile-based shading classification. So in short, this is optimized. We have optimized shader variations of our clustered lighting, which only have 1, 2, or 3 shading models. We have 14 combinations of these. The screen is divided into 8 by 8 pixel tiles. Then there's a classification pass in compute, which checks for the needed shading models for each tile. It writes the counts and indices for each of the shader variations, and then it does an indirect dispatch only for the tiles of that specific variation. Our terrain was also something that we wanted to improve on visually. This is an example of original Sin 2. The geometry was divided in patches. These were separate draw calls, which is not that great. It was 64 square meters with 1 vertex every 2 meters, which is also not that very detailed. It uses a base material, which was able to blend based on the slope using 2 texture sets, so that was a pretty nice feature. But then we had painted materials on top of that, which could be any material, which is nice, but this meant a unique draw call per layer, which is not so nice. And then our geometry was, well, there was extra geometry where we painted, luckily only there, but still also not so good. And everything was alpha tested as well. So we wanted to improve that. So for BG3, we have the geometry still in patches, but now it's an instance draw call. Same size, but 1 vertex every 1 meter, so 4 times the amount of triangles. But there's also an extra center vertex, so we have 16 times the amount of triangles. This didn't add anything in our height map data, so it was relatively cheap memory-wise. But this helps with the very steep transitions, so they're a bit smoother. And this meant we had no more draws per layer. But because this is an instance draw, we cannot do hole rendering anymore, well, or cut holes in the terrain. So we had a separate hole data flag per quad. And for this, we basically just set the center vertex to not a number, which is kind of a hack, but we call it a creative workaround. So that causes all those triangles to not be rasterized. We used an engine-side shader this time. So we used terrain brushes which have a texture set and some properties to do the blending, height-based. We allow a maximum of 4 layers to be blended per pixel, but we allow many more layers in total. And for that, we use a keys map. This is generated in the tool set from the painted data. And this gives us the 8 most contributing layers for each pixel in that keys map. And this is done at twice the resolution of the height map. Some more image quality improvements we made. So we noticed very quickly when trying to do the first cinematics that flickering pixels were very annoying and distracting. So we added temporal AA. We also added specular AA on our roughness. And we also fixed some artifacts and bugs in our depth of field. And we also, at the same time, bumped the quality a bit by adding a circular bokeh implementation. And all these improvements helped in getting a more filmic look and less gamey look. So here's some examples. If you look at the shoulder, there's a lot of pixels of the in focus character bleeding into the background, which flickers. I hope you can see it on the screen. So that was fixed. And then another thing that we fixed was the aliasing in the background there. So we used the temporal filter to stabilize all of that. So now it's nice and smooth and no more distractions. We also improved our color grading and improved our display rendering transform. Early access initially shipped using ACES 1.1, but this had a couple of problems. For instance, the blue highlights turned purple. We fixed that. but it also still had other problems like visually it kind of looked yellow and the blacks were very crushed. So our colleague that worked on this joined the ACES Next Output Transform Visual Working Group to work on the next iteration of ACES. And from that, we had a very custom implementation of ACES 2. It's not released yet, but so that's why it's within quotes. So this is 80% the version 11 prototype, 5% the 9, and about 15% is completely custom code. So things looked a lot better. So on the right, it's less contrasty, and you can see that there's a hue shift as well, which was actually good in a sense, because that character on the right is actually the albedo color in the textures this time. But art also compensated for these hue shifts. So it didn't look as intended anymore. The character was supposed to look a bit more yellowish in this case. So we had to introduce a hack in the new version to kind of compensate for that again, so that the red highlights were more yellowish again. This is something we will obviously remove in the future. Then, lighting-wise, this was very important in our cinematics. So this is without lighting. This is with lighting. So it's a bit like in film. There's lighting setups on all of the characters. Some of these are automatic. Here you can see an example of all these setups. It can get quite complex. But so some of these are automatically placed. We have a bunch of presets for this. We also need to accommodate all the different lighting conditions that these dialogues can play in, because any dialogue can be played in very much any location in the game. So this also is used in gameplay. Every character during gameplay also has the 3-point lighting setup, and this is without lights. And the character in the back, you cannot see it almost, and this is with lights. I hope you can see the difference on the screen. So it makes the characters pop out a bit more. Yeah, and here you can see all those lights in a debug view. But this gives us some problems because, well, first of all, we need a lot of shadows. If you look at this character, for example, it looks kind of flat, even though there's extra lights. And this is with shadows enabled, and there's a lot more depth, and the extra rim lights, well, that were added, they are not bleeding in to the front of the character anymore. And we also needed shadows on alpha blended objects. We didn't have that yet, and well, then you get issues like this. There are transparent parts around the eyes, and they're standing in a cave. Sun is at very high intensity, and well, without shadows, they look a bit like zombies. And this also this followed us towards the end of development, even the fact that lights need shadows. As you can see here, there's highlights inside the mouth, which can be quite distracting as well. So we always needed to make sure that all the lights on the characters had shadows enabled. And to support this amount of shadows, we implemented tile based on the directional shadows. So in short, this is an atlas where all the shadows are packed in tiles. For the omnilights, we use a tetrahedron shadow map. So it's only 4 faces instead of regular 6 with the cube map. And this packs nicely into a single tile, so each light is occupying only 1 tile. It also only has 4 faces, so there's less draw calls that we need to do twice when they overlap different faces of the tetrahedron map in this case. We vary the tile size based on size on screen, distance and such, and well, maximum these are 2K each, or 512 on low settings. And this meant that all the lighting could now be done in our main clustered lighting pass, because before that we had to do separate lighting passes for each shadow casting light. And this also meant that we could use exactly the same lighting on our forward pass for the alpha blended objects, so that was also very nice. And that fixed the eyes of the characters then. But then there was a second problem with these light setups. So the characters move, and they would move outside of their lighting cones. Obviously, you can make the light move with the character, but with cone lights, this is quite difficult, and also there were the tips of the cones of the other character were inside the other the character that he's talking to, so yeah, that was quite annoying. So we had a few fixes for that. First of all, we added the directional light type, which we didn't have yet. So pretty straightforward, but we also added support for cookie textures, so we could cast these nice shadows in caves without any performance overhead of having to render shadows for those lights. And a third problem was that these lights were also affecting the scene and, as I mentioned, other characters. So here you can see that, and this is with the fix enabled, and the fix is that we added some channel masking, so every light has a certain mask, and then characters and environment has another mask, and then we can filter out what we want to cast the light on. So this is a few times back and forth. So yeah, we needed a lot of fixing for just adding some lights in cinematics. We also improved the sky rendering. And you might think our game is mostly top-down, and in cinematics you don't see the sky that often. So this was not really needed for the game itself, but it was mostly needed for development. It prevents recreating a new sky dome every time when artists want to change or tweak the lighting. For that, we kept it quite simple. We added atmospheric scattering, support for stars and moon rendering, and also volumetric clouds, but still quite a basic implementation. These could also cast optionally cast shadows onto the world as well. So this was more than enough for what we needed. And this is an example of a cloud coverage map, which we also added, so artists could paint freely where they wanted shadows and where not, so to get these nice overcast atmospheres. And then perhaps the most impactful change that we made visually was adding volumetric fog. This was not initially planned, but the quality was just not good enough yet, we felt. So we added a Froxel-based implementation with 2 global fog layers, also local fog volume support, and then we added controls for color, density, height, noise, etc. And this is an old screenshot of a regular depth-based fog. So as you can see, things look quite flat. You could move the fog more to the foreground a bit if you wanted to, but then it quickly drowns out all the lighting. And so here's another scene. Why another scene? Well, I couldn't really compare anymore with that old scene. So I photoshopped depth-based fog just to show you the difference. And this is with volumetric fog. And as you can see, it bumps the quality a lot. So you can now feel where all the lights are, even lights behind the building, for example. You can really feel the fire, the blue glow of the tree there. And this is an example with local fog volumes to add even more atmosphere. This also gave us a free VFX lighting approximation, basically. We are using the in-scattered luminance from the fog to light all the particles. So that was a nice extra. Then, of course, split screen, which is one of the key features of our game. As you can see here, I tried to enable a viewport, but things were not going as planned. So everything looks kind of broken. Everything is shifting. You can see the VFX there also not being aligned with the character anymore. The outlines are broken. Even the eyelashes of the character, I think, are moving there. So there's a couple of things you need to pay attention to when working with multiple viewports. All quite straightforward, but you need to, well, pay attention that your render target and viewport width is not necessarily the same. You also need to manually clamp sampling locations, because you cannot rely on the sampler state address mode all the time. You need a per pixel position, when you use pixel position or thread index, that doesn't always equal the output position anymore. Downsampling is also making things more difficult, because things can start bleeding into the other viewport. And tile-based techniques, well, they often need an extra row of tiles on the edge of the first viewport. So, and then also resolution scaling techniques like DLSS and FSR are a very fun extra in the mix. So then some technical changes and optimizations. Here I will discuss the things that people mostly don't see. So like the new rendering features. So this is more the things that are happening behind the scenes. But the first 2 features are actually things that you do see in the game, but the technical implementation behind it is maybe a bit more unusual. So the first one of these is fading. And what do I mean with fading? Well, characters in character creation need to fade, but also objects when you walk behind them, or when you enter a building, suddenly an entire floor needs to disappear. So how this is usually done to fade opaque objects is with a dithering pattern. So what are the disadvantages of this? Well, that means that every material's depth pass would need a pixel shader clip or discard instruction. This disables early Z, and you also get this visible pattern. So to solve this early Z issue, we use the stencil buffer. There's no pixel shader modifications needed anymore. And we can just swap the depth stencil state for fading objects. So we had different PSOs for these saved in our cache. And so we have a fill stencil pass that fills the stencil buffer with a 4-bit ordered different pattern, like you can see here. And then we set the stencil, for this we set the stencil function to always and replace on pass. So it just fills it up with the stencil ref value. So for this we use the SV stencil ref on the hardware that supports it. And as a fallback, we do one draw for each bit that we want to raise, and the pixel shader then clips based on the pattern. So that gives us the dithering pattern already, but we also wanted to, well, this is the stencil test, so it's just the opacity value of the object converted to 4 bits, and read mask also to those 4 bits of the pattern, and then function is greater, so then you get the dithering pattern. But we also wanted to solve that you see this visible pattern. So this was a bit inspired by the following inferred lighting paper. This uses a discontinuity-sensitive filter to reconstruct lighting from low res to high res. But also, it used the stipple pattern for transparent objects. And using this same filter data, they can simulate transparency. So I thought it was interesting. So we modified the stencil approach. The stencil fill pass now sets bit 5 to 1, bit 6 to 0. And we also modified the depth stencil state that's using to fade objects, as you can see here. Most important result of this is that in bit 5, we now get an inverse mask of where fading objects are rendered, and bit 6 gives us the stipple pattern of the dithering pattern, the pixels that succeeded basically of that object. Why an inverse mask in bit 5? Well, basically because there is no such thing as a set 1. We could increment or decrement, but we wanted to support multiple objects fading on top of each other. So we used set 0, and that's why the mask is inverted. So this is this is an example of an end result. So as you can see, not that many pixels succeeded in this case because it was very transparent. That also results in a quite low resolution blend, but usually the blending goes really fast, so you don't notice this. And to achieve this, we have a fade blending pass. This is a compute pass during post-processing. Input is the lit scene and the stencil buffer. It then checks in a 4x4 neighborhood for this pattern. And it performs blending or not based on bit 5, and it drives the opacity based on the ratio between bit 6 and minus bit 5, 1 minus bit 5. For the color, we sample a 3x3 neighborhood to prevent an image shift. And we collect foreground and background pixels. We expand to 4x4 if none are found. And we blend the foreground and background. Then with, the foreground pixel blends with the average background, and the background pixels, they blend with the average foreground. And this is an example with a bit more pixels that succeeded the test. So as you can see, resolution increases. This is a slow motion example of characters. So it's not always that noticeable that it's low resolution in the beginning. But this gives us a nice fading without dithering. Well, without visible dithering. Second feature is our surfaces. So we have many gameplay surfaces spawning in very noisy patterns. So we can have blood, water, ice, fire, poison, many more. And these are deferred decals with some effects spawned on top. These decals, however, they are rendered in quite unusual way. This is not a simple shape always, as you can see with the water there. They can take any form, grow, shrink, take over another surface. They can grow quite large as well. So this is the gameplay data that we get from our AI grid. It just tells us for each cell where these surfaces are. So what can we do with this for rendering decals? Well, 2 options. We can render many small decals, 1 per tile, but getting smooth edges then is quite difficult unless we spawn slightly larger ones and just basically splat them over each other, but that's a lot of overdraw. We could also render a larger decal using a texture mask, but And that gives us smooth edges because when we use linear filtering. But the surfaces can grow, so do you then grow the decal, or do we render multiple larger ones, but then you get seams? So this was kind of a difficult problem to solve. So we thought, like, well, even with the masks, the empty space turned out to be quite costly. Because for deferred decals, you need to sample the depth buffer, convert the depth to world space, then to AI grid space, to then sample the surface mask texture, to then see that there is no surface and then early out. That's not really a good early out if you need to do 2 texture samples for all the empty areas. So 1 large decal per surface type was definitely a no-go, no large decal over the entire terrain. So how did we do this? We dynamically generate a mesh based on the surface mask, but not in 3D. Instead, we're generating screen space tiles. We use a fixed shared vertex buffer of all the tiles. The index buffer is then generated per surface type with a compute shader. For every pixel in a tile, we check what surfaces are there. For each surface type within a tile, we then write indices if the surface is present, or we write 0 indices so they're not rasterized when there is no surface of that type. And this gives us the nice benefit that only pixels where the surface is actually visible are causing these tiles to be generated, so it's automatically, well, culled, you could say, when it's behind other objects. And this means that we don't even have to do the typical depth stencil test anymore, depth stencil test for deferred decals. And it looks a bit like this. So as you can see, there's a bit of padding space for each surface. This is because artists want to be able to distort the edges. And this is a view from a bit farther away. So as you can see, there's quite a lot of decals, and as soon as gameplay starts there and there's combat, for example, things can change very wildly, so this helped reduce performance overhead a lot. Some other optimizations, real quickly, because I'm going over time. We added a frame graph. In those two, we had to know which render target or buffer was available for use. So we implemented the frame graph solution. This is the dependency graph. We built each frame. We know this knows all about our render stages, so render targets and buffers, frame buffers, and so on. And to rebuild it, it checks which render stages are active, builds a lifetime matrix, so it checks the usage of each render target or buffer in each render stage. Then it checks how long each render target is actually needed. It deduces the memory requirements from this. And this also handles auto-resizing of render targets, so following the output resolution of your window, and it handles upscaling as well. It also handles barriers between render stages, and we use memory aliasing for Vulkan, DirectX 12, and PS5 using a memory slots strategy, and for DirectX 11 we use just a resource slots strategy as a fallback. Virtual texturing was also something that I mentioned. So we use a dense world with a lot of unique objects. So texture memory would have been a problem with regular MIP streaming. So we implemented virtual texture streaming using Granite SDK by Graphene, which is now part of Unity. All texture data is split into small tiles, basically. The gbuffer writes VT feedback data to know which tiles are needed. We limited ourselves to 1 VT sample per material. And this is using 3 layers, so base color, normal, and then all the physical properties. So the CPU does a readback of this to know what tiles to stream in. And this is nice because we have a known fixed memory budget, CPU and GPU cache. And this was different depending on the graphic settings. We also added lots, of course, and HLOTs. So we started using the mesh slot system again. We worked together with TechArt for this. Our mesh importer generates slots automatically using Houdini. And the HLOT system, well, the world is divided into tiles. All the geometry and textures within the tile are exported to Houdini. Houdini outputs a single optimized mesh with the unique textures. This runs offline overnight. But this had one problem. This didn't take materials into account. So some materials have color variations, like you see here. The rocks have a gradient in there based on the world space position. Some others use random colors, like for the trees, for example. And yeah, materials are sometimes just way more complex than just using some textures. So what we did to fix that is we bake down the material for every local instance before sending it to Houdini. Houdini uses those unique textures then to put everything together into the HLOT. Occlusion culling, we also added. So we lowered the triangle count, we lowered the drawcle count, but it was still not enough. So we didn't have GPU side culling and no indirect drawing. So occlusion culling on the GPU would mean a readback on CPU and frame delays. A big refactor there was not really planned. So we did occlusion culling on the CPU using Intel's masked occlusion culling library. CPU rasterization of low detail occluders was done on the CPU, and then you get a high Z buffer, and objects are tested against this high Z buffer. For shadow occlusion culling, well, we still had a lot of extra draw calls there. We couldn't spend the time on CPU for that. So we did do a readback here for the GPU and lived with a frame delay. It was still a win, and we had no shadows popping because, well, our sun doesn't move, so that was a nice benefit. And every X amount of frames, we downsample, so we downsample the depth shadow maps, read back on the CPU, and we use it in the same way as for masked occlusion culling. We also added vista shadows, because after we optimized all the shadows, of course, what did the artists ask? Hey, can we have shadows everywhere? So for distant shadows, beyond the dynamic castigates, we have the vista shadow system. The world is divided into sectors. This is centered around the camera. Only one is rendered each frame. The vista shadow map is swapped when all the sectors are rendered, so these are basically static shadows. Here are some details of it. So we have detailed level, broad level, 280 sectors total, and this had very little performance overhead. We also added a compute skinning pipeline, so all the skinning is done in the beginning of the frame. All bone transforms are done only once per object. This gave us less vertex shader permutation, so less PSOs. Blend shapes, this was very late in production. It was only used for slight adjustment to facial expressions. For this, we also did the same thing, so in the beginning of the frame, around the same time as the skinning, also in a compute shader. So how did we keep track of all of this? Because there's a lot of new features, both rendering features and technical changes. Well, we have a QA portal and benchmarks running. This gives us detailed information about, well, almost per day. We can see if performance went up or down. It tracks memory and all sorts of things. So this was a very, very handy tool for us to see if we accidentally submitted something that, well, broke things, because that sometimes happens. So what are our conclusions? What went right and what could have gone better? Well, adapting of the modern APIs. We didn't entirely reach our goal. It was very hard to switch the toolset API during production. Stability of the toolset is very important. The toolset in DirectX 11 meant that Vulkan DirectX 12 was still partially DirectX 11 style. We didn't want diverging code, so we couldn't use much of the new capabilities, and this also held back some optimizations. But most importantly, well, I guess it worked. So it wasn't all that bad. The CPU was also faster. So yeah, a bit of a win and not a win there. What about the new and improved rendering features? Well, I think you can say we reached our goal there. We improved shading, we improved image quality, lighting, terrain, atmosphere. I know we're not using latest and greatest techniques everywhere, but this was not our goal. Our focus was on what our game needed the most, which was the new cinematics, and, well, I think we reached our goal. Technical changes and optimizations, so we also reached our goals. We have far view distances, more objects, more triangles, more texture detail, and we are within performance on target performance on all the platforms. And not something that we did, but something new during this project was a tech UA team and the QA portal, which we are very happy with and will definitely use a lot in the future. So what about the future? What about Framework 5? Well, big changes are happening now. For the first time, our engine team now also has pre-production time. So we were very happy with this. This allows us to throw away old code and rebuild from the ground up. We can make drastic changes to rendering without affecting existing art. And it's not always super bad if something would be temporarily broken in the toolset. So what are our main focus points now? We want to go for a fully bindless GPU-driven render pipeline. We are experimenting with meshlets and mesh shaders, and we are also looking into fully dynamic GI. And this is already done. So we are finally rid of DirectX 11, and, well, Vulkan we don't use anymore. So, and this, yeah, that's top secret. Special thanks to everybody that worked on graphics. I hope I didn't forget anyone there. Also, additional thanks to the companies that helped us with other platforms like Stadia, Mac, and Steam Deck. And thank you to the organization as well for hosting this in this nice building. To be looks a bit like the Sponza scene, so it's perfect for graphics. And these are the promised references. And thank you. We are also hiring. We're looking for people in all skill levels. Also open to accept interns. So if any students are here, definitely welcome to apply. And yeah, I'm a bit over time, but I think we have time for a few questions.
No, I think we have perfect timing so far today. Yeah, I'm taking questions. I'll start from here.
For volumetric fog, you mentioned you're using 2 global layer. What is the purpose of that? How does it work?
Excuse me, can you repeat the question?
For the volumetric fog,
yes.
You mentioned you're using 2 global layer.
Yeah, so as I said, we have controls to control the density of the fog, the color and such, and sometimes they want to add a height fog somewhere and also distance fog, like for the atmospheric effect. So that's the 2 layers, basically.
Hey, huge fan of Divinity Original Sin, and definitely put in a lot of hours into Baldur's Gate. I've been playing on Steam Deck, and the visual quality is quite different from what you presented. I was curious what features you had to disable for that platform.
Well, basically we dialed down the settings, so I don't think we had special optimizations running only on Steam Deck. We just, yeah, didn't set everything to ultra, basically. So I think if you go to the PC version and dial everything down, you should see something similar.
Okay, thanks.
Yeah.
Hi. First of all, great slides, and thank you so much for showing one line at a time, so I can draw the attention to the proper place, like super cool. Okay. Regarding my question, you've said a lot about issues with rendering that happened. I was wondering how much of them you were able to catch during the development, how much of them appeared after early access release, and then how much of them happened after the full release?
That's a bit of a tough question, like quite a broad question. Well, for early access, we first focused on getting the cinematics to look right. Of course, there were some glitches here and there. We had trouble with, for example, getting everything frame perfect when switching cameras. So sometimes characters would still be in T-pose for one frame or things like that. So we put a lot of effort in that during early access, and then for release, we tried to get everything smooth. Regarding other graphical artifacts, yeah, we just tried to fix them as soon as possible, I guess. So it's not, I cannot put an exact number on how much we fixed before EA or during or after.
Yeah. Yeah. But generally, great job, because on the both releases, the rendering was super cool. So I was wondering, like, the platform you mentioned must have worked super good in terms of like catching all the errors that you have in the rendering. So great job. Yeah. Thanks.
Thank you.
Hi, thanks so much for the talk. That was great. Could you elaborate a little bit on how you did the screen space decal tiles to the actual shape of the decal? Because you were mentioning the issues with like really small decals overlapping or big decals with the seams.
So yeah, we basically wanted the more exact shape of the decal because of, well, the early out wasn't really working for us where there was empty space because we still needed to sample the depth buffer and the surface mask texture. And rendering smaller decals was also not beneficial for overdraw. So we thought of generating a mesh for that closely matches it, but the screen space idea just came from, I think we were at the same time working on the tile-based classification as well, so we thought, like, why can't we do that for decals? So we basically do the same tests as we would have normally done, so we read the depth buffer, then we convert it to the surface mask texture, see what surface is there, but now we only have to do it once because there is no overdraw. And then also, yeah, the decal rendering afterwards is really cheap.
Thank you.
Yes, I quite like the pace of the presentation. Very blink and you'll miss it. So my question is a bit more open-ended on the management side of things. You mentioned that over the course of development, there were a lot of features you decided that you needed. There were also teething issues with kind of developing the features, getting your artists to use them, etc. So I was wondering if you could share some advice on the creative process, as it were. Why did you deem a feature suitable? How did you go about experimenting? How did you go about convincing the artists to use them? And how did you end up with them in the final product?
Well, so first, we had our visual target, so we knew what we were going to do. We knew that we wanted a more close-by camera, the cinematics, etc. So there were some obvious changes that we had to do. But after that, it's basically, we see where we end up. So we try to apply these changes, and if anything is still not good enough, then we try to reserve time for that in our planning. So it's not always easy, because planning often changes then. But there's a lot of, like I said, a lot of communication with the other teams. So artists come to us sometimes asking a random question, like with the shadows, for example. We want shadows everywhere. Of course, we saw that coming, but there were other things that, yeah, sometimes they just ask, like, hey, would there be time for this feature? And then we just weigh the pros and cons, like how much would it benefit our game? Because obviously every new rendering feature will have some improvement, but we always try to see what our game needs most. So if it was related to cinematics, then very often we did it, because, well, that was a main focus point of ours. Other things, like, I don't know, if somebody would ask a more specialized shader for a certain rock or something, that's obviously something that we didn't do. So
okay.
That's usually how we go.
Very clear, thank you.
We have one more question.
Hello. It sounds like you have a lot of tough decisions to make, and I'm wondering how exactly you come up with the solution, what to make and what not to make, because it sounds like a lot of chaos for the most of technical decisions that you mentioned, changing the platform, coming up with a tech QA team, a QA platform. Do you make these decisions like a team, or you have a boss with a strong hand and he says, we'll do this and that?
Well, of course, we have some structure in our company. It's not all chaos. Well, we grew quite a bit, so we were, I think, well, I'm not entirely sure, but I think we were around 100 people or so, 150 maybe in the beginning, and now we grew to, I think, 400, 500, 400. So there's more structure now than we had in the beginning. It was a difficult exercise as well. So, of course, well, there's my colleagues here. If you have more management questions, I guess you can probably get better answers from them. But of course, it's, yeah, things like, hey, we need a QA portal. That's obviously not like, hey, somebody just does it. It's yeah, there's meetings with different departments, meetings within departments, and yeah, these things are just consequence of that.
Okay. Thank you very much for the lovely talk.
Thank you.